Okay, today we're going to talk about rational functions. So these are what we call expressions. Why when you look at this list do you see expressions? What about them says, hey, I'm an expression? The fact that so there's exponents, there's variables, there's no equal signs. So these are not equations. We are going to get into rational equations at another time. And so our very first thing that we're going to do with the rational expressions is try and talk about, well, what are they? And then we're going to get to simplifying them in different ways. So an expression that's called a rational expression can be written as a polynomial divided by another polynomial. So something to know about polynomials. Polynomials all have variables with whole number exponents. And then when we talk about the domain, you cannot have 0 in the denominator because we were talking about that before. What happens if you divide by 0? Let's say there's $8. Remember I gave this example. And if you divide it by 0, how much does that person, can you divide up $8 0 times? I mean, actually, I guess you could divide it up 0 times. You still have 8. But let's say you have 0 people want that to split up that money. How much does each person get? Well, since there isn't a person, somebody's going to come along and is going to want the $8. So technically, if $8 exists, it's being divided by 1, right? Because someone wants to claim it. And so every whole number has a denominator of 1. Every number that is not a fraction essentially has a denominator of 1. Or you can make a number into a fraction by putting a denominator of 1 underneath that number. Okay, and then we were talking about polynomials. So polynomials, an example of a polynomial could just be, in this case, 1. There's no variable here. And x, this is to the first power. N, here, this is also to the first power. Here you have a squared. So if you had something like a to the 1/2 power, we would say, and that's supposed to be an exponent, that would not count as a polynomial. So not a polynomial. We see all of these examples above are polynomials. By the way, a to the 1/2 power is the same thing as the square root of a. So we can see that this is not going to be a polynomial either. If you had a negative exponent, x to the -1 power, you could make that into 1 over x. Now that would have a positive exponent. So when it has a negative exponent, it wouldn't count as a polynomial. But then you could use the idea of what does the negative exponent really mean. Okay, let's look at an example here. So we have c of x is 250x divided by, now here's another thing that's important. When you type this into Desmos, you might sometimes need to make sure you have parentheses. There's an implied parentheses because the whole entire 250x is being divided by the 100 minus x. This represents a rational function that describes the cost in millions of dollars to remove X% of the pollutants that are in a river. So if we wanted to determine the cost of removing 40% of the pollutants, we would say, because they're saying X is the percent, that X is equal to 40. So if I wanted to do that, am I actually solving or am I evaluating? Remember, we've talked about the difference between solve versus evaluate. Am I solving for X or do I have X? I have X. So what will I do to find out the cost? Exactly. We're going to plug in 40 wherever we see X. So we get 250 times 40 divided by 100 minus 40. Okay, so let's figure out how much this is. 250 times 40. Oh, let me get out my tiny little calculator here to help me with that. 250 times 40 gives me 10,000. And then what's 100 minus 40? 60. So I'm going to take 1,000, I'm going to divide it by 60, and I get 1.66 and then 6 repeating. So how could I interpret then how much money is it going to cost? Is it going to cost me just $166 to take out 40% of all the pollutants from the river? What do you think? Somebody give me a sentence answer. How much is it going to cost? Oh, because we see that the cost was in millions. So you referred back to the problem. So it will cost $166.6 million to remove 40% of the pollutants from the river. Okay. So that's just an example of a word problem where we might see a rational function here. Another example that I have created with some students is like, I have this idea that sometimes, does anybody ever like to, let's say you like to go to a yoga class. Oh, just going to make that up. Okay. So for instance, I joined this yoga studio for 30 days. It was $30 for 30 days. And that was unlimited. So I could go as much as I want. Well, they happen to have this star chart. And every time I went, I could put a little star next to my name on the chart. So I ended up, every time I would go, I'd think, well, how much money am I spending for every single class, right? I mean, if I went to the first class and I only went once for that 30 days, then I would spend $30 for that one class, right? That would be the same thing as $30 divided by one class. I spent $30. What if I went to 2 classes? How much did it cost me per class? So divided by 2 classes would mean I paid $15 per class. And by the way, you guys, the word per, it really does mean divide. See, $30 for 2 classes, $15 per one class, right? So if I made an equation out of this, if I said, I'm going to go to X number of classes, I can't go to 0 classes because I showed up to the class and I paid for the class, right? I paid the $30. So we would not divide by 0. It wouldn't make sense to say, well, what's $30 divided by 0? So in this case, my X has to be greater than or equal to 1. And actually, I can't even go to a fraction of a class, so there's probably another way we could say, I have to really only have whole number or natural numbers here. I couldn't go to fractions of classes. But the more classes I go, what's happening to the cost per class is it's going down every single time. And you can kind of see that. And we're going to look at the graph of some of these in just a moment as well. But the idea is with a rational function, we were talking about domain before. With a rational function, you don't want to have what? What kind of x's do you have to exclude? You can have negative values of x. I mean, in that example, you couldn't have negatives. But for here, let's say if I just have an equation, I wouldn't have what? 3. You wouldn't have 3, so you had to have x such that x cannot equal 3. Why did you choose 3? Exactly. You can't divide by 0. So if we were to take f of 3, you would see we would get 5 divided by 3 minus 3. We would get 5 divided by 0, which is undefined. Okay? So to find the restriction on the domain, what numbers you can't have, you're going to set the denominator equal to 0 and solve for x. So right here, right away, can you tell what numbers are going to give you 0? What should you do to find the domain of the second problem? Any thoughts? Make the denominator equal to 0. Exactly. So we take x squared minus 3x minus 4, and we set it equal to 0. How am I going to solve for x in an equation like this? Yes. Well, what am I doing here? I'm getting ready to We're factoring. So we solve a quadratic because that's x squared. We have to solve it by factoring. So what two numbers multiply to negative 4 and add to negative 3? For negative 4, and what should the sign on the 1 be? Positive. Does that work out if you were to FOIL it? Now, we haven't solved it yet, have we? So what values of x could I have? X would be, and positive 4. And that means my domain is x such that x cannot equal negative 1 or 4. I don't want to have either one of those numbers because that's going to give me 0 in the denominator. And you'll see if you plug in h of negative 1, you'll get 0 in the denominator. If you plug in h of 4, you'll get 0 in the denominator. So we really want to look at these on Desmos. And so I've set up my Desmos already because I figure otherwise it kind of takes too long. And the cool thing about Desmos is, like I said, you can sign in, you can save these graphs. This one was from a different problem that I didn't need. And then you can turn on the graphs as you need them. So if I click that little button there, we're going to see, and I'm going to just zoom out. And we can see what that picture is. What do you think is happening here? It's like going down, and then this one's going, down here. What's happening at this area? It's showing us the numbers it can't be. If we plug in x equals 3, you see we get a vertical line. We were talking about with domain the idea of a vertical line test. So this vertical line, x equals 3, is not crossing. And if we start to even zoom in, if we go way up, you're going to see that the red graph is getting very close to that number, but it's not touching it. Okay, so let's turn that one off. We're going to turn them both off. And let's turn this one on. This is the one that we just found. And so again, if I were to take and make an equation, x equals negative 1, you'll see what we call that is an asymptote. It's not part of the graph. It's where the graph is going to get really, really, really close to that number. And then it's going to say, wait, I can't be that number. I can't divide by 0. So we're getting really, really close to what's called a vertical asymptote. We have another vertical asymptote if I graph x equals what? Say it. 4. If we graph x equals 4, we can see that we have another vertical asymptote. So I'm just graphing those so that you can actually see those lines, but I'm not. That's not actually part of the graph because remember we said that is excluded from the domain. Okay. Any questions on how we find the domain for rational functions? And how to graph that on Desmos?